So it turns out we have very good optimization packages for solving that. Okay? The positive set of definitions is a convex set. You can optimize objectives over that. Convex optimization, some people use it to say the problem is solved once you find a convex relaxation. I won't go that far, but I'll say that it means we get, if there's a solution, we'll get it efficiently, and we'll get the global solution, okay, unless the number of decision variables is comically too large, or the conditioning of the problem. There's a few things that can still go wrong, but finding a convex formulation is normally a pretty good thing. There's still a gap that I just want to sort of as a disclaimer. Not every positive polynomial can be written as a sum of squares, but most can. And for the purposes of the Lyapunov analysis, we assume that there is no, we basically act as if there is no gap. You can almost always find, there's some theorems that are emerging now saying that any stable polynomial system should have a sum of squares positive Lyapunov function with even a sum of squares derivative. Okay, so let's see if we can take the sum of squares analysis, the ability to search over positivity of polynomials, and use it to automatically discover Lyapunov functions. Okay? So if I give you a polynomial dynamical system, now if you want to prove it's stable, what you have to do is search over Lyapunov functions which are positive, that's a sum of squares constraint, and such that the derivative, which is the gradient of a polynomial is going to be a polynomial times another polynomial. This is still a polynomial less than 0. That's just two sums of squares constraints. And we can use sums of squares optimization now to discover a V that proves stability of the system. It's not just for polynomials. The theory is deeper for polynomials, but we do it for trigonometric functions by working on the quotient ring and doing all these extra things too. But so if I were to work that exact example now with sum of squares, so I have V equals x squared, right? I'm not even going to bother making a sum of squares constraint on that. I know x squared is positive, okay? But this one is a little bit more subtle. Is this thing, the question is this always greater than 0? Well, I don't want to ask that question. I'm going to ask an almost equivalent question. Can I write a sum of squares decomposition of that? It turns out I can't, right? This thing isn't always greater than 0, but I can play one more trick to ask, is it greater than 0 just in the domain -1 to 1? And I'm going to just put it up quickly, but you can restrict the domain in these optimizations using things like the S procedure, which gives you, I'm not going to go through it, but it gives you another simple, it's like a Lagrange multiplier problem, another simple sums of squares problem that you can solve. This is restricted to that domain, and that will say yes. I can find the region of, I can search over the Lyapunov function by putting 3 parameters in my Lyapunov function, and then asking to maximize the